Hey folks, today we're going to talk about Punnett squares. At this point, you know all you need to know about pedigrees, but how can we predict from one generation to the next how likely an individual will be to have a person who has, have a child who has a particular affliction, depending on the genes that they have? Now, to review a little bit, we know that there's a couple of terms that we've been using over and over, like genotype. That's the combination of genes an organism has, the actual genetic makeup. And they're represented by letters. The capital letters are dominant, the lowercase letters are recessive. An individual who has a mix of the two is heterozygous, and a person who has both of them have homozygous. The phenotype is the result from the genetic makeup, the physical appearance that we see in the individual, such as the trait of purple petals versus white petals, freckles versus no freckles, so on and so forth. And depending on these mixtures of genotypes and phenotypes, we have a bunch of different alleles we could have from each generation. So if we have a dominant allele, that means that the gene prevents the other allele from showing up, the recessive allele from showing up. So if it's present, then no matter what, the phenotype will show. If it's a recessive allele, then the gene that does not that is there does not show because it's being masked by the dominant allele. So you must have two of those lowercase letters for that gene to show. Some examples to review us here real quickly here. We have straight thumbs and straight thumbs being dominant to hitchhiker thumbs. If you recall, we used a capital letter for the dominant straight thumb, capital T, and a lowercase t for the recessive hitchhiker's thumb. If we combine those two alleles and the possibilities that we have, we'll have three different possible genotypes. Two capitals, one capital, one lowercase, and two lowercase. Based on this, the only one that could have the hitchhiker's thumb would be an individual that has a lowercase t, the phenotype being the hitchhiker's thumb. Everyone else has a dominant allele, and therefore the dominant allele shows up in the phenotype. That would be the straight thumb. Let's do this one real quickly together here to cement in our minds. We have a capital P and a lowercase p. The purple petals are dominant to white petals, which means that a capital P is going to be the dominant allele, the purple petals. And the lowercase p is going to be the recessive allele, the white petals. That means, of course, that the capital P genotype has to be purple. If we have a capital P, lowercase p, the capital P is going to mask the recessive allele, and therefore that's still going to be purple. But in the case of two lowercase p's, we have white petals because neither of them are dominant. To review a little bit more vocabulary, if both alleles are the same, we call that homozygous or purebred. If you have a purebred dog, that just means that they have their genetic makeup traced over and over and over again to have the same breed over and over again. In this case, it's the same allele over and over again, the capital T's or the lowercase t's being homozygous dominant or homozygous recessive individual. If the alleles are different, however, we call that a heterozygous. We could also call that a hybrid meaning a mix of two things. So this capital T, lowercase t is a heterozygous individual. The dominant allele will still show, but the recessive allele is there behind the scenes. Now, what if we decide to cross two people together? Two people that we know the genotype of. We can then use what is called a Punnett square to predict the possible genetic makeup of the offsprings, meaning that I can predict exactly how those kids are going to look if I have 100 of them. How many of them are going to be heterozygous, how many of them are going to be homozygous dominant, how many of them are going to be homozygous recessive. So in this case, I'm crossing one parent that has a heterozygous genotype, the capital P, lowercase p, and another parent, getting on with another heterozygous, capital P, lowercase p. And each of these boxes are going to represent the possible offsprings that we have, meaning that this particular parent might give this genotype, and that could result in either of these being laid out here. And this parent could give this genotype, which means that this letter could be in those boxes there. So if I cross the capital P's together here, in this box I have capital B, which means I have 1 of 4 chances of having a homozygous dominant child. In this box here, we cross the capital P and lowercase p. Remember that the dominant letter always goes first, regardless if it's parent 1 or parent 2. So this would be a heterozygote individual. So a 1 in 4 chance of being a heterozygote. Take a look down here, though. Capital P, lowercase p, that's going to result in another heterozygote. So it looks like 50% of the time, I have an individual that's going to be heterozygote from these 2 heterozygotes being matched together. Finally, this last box, we have a lowercase b, 2 recessive alleles down in this box here. That would be the homozygous recessive there. Looks like it's 1 box of the 4. That's a 25% chance. I now know exactly the chances of my kids having, let's say, freckles or no freckles based on the genotypes of the parents. And in this case, we know that the colors of the flowers are going to be dependent on the genotypes and the dominant allele that shows. So these 2 dominant alleles are going to give us a purple flower. These 2, with the recessive allele being masked, is going to be a purple flower. That one's also going to be purple, and this one's going to be white. Looks like of every 4 possibilities, 3 of them are going to be purple, 1 of them are going to be white. That means that I can figure out what is called the genotypic ratio and what's called the phenotypic ratio. Basically, I can figure out how many of each different kind there's going to be of each of the letter combinations compared to each different kind of the phenotype combinations. In this case, there was 1 capital P combination here, so that was the 1 in front there. 2 of the heterozygotes, and 1 of the homozygous recessive individuals. For the phenotypes, however, these 2 are going to be combined to make 3 total, because there's 3 purple flowers to every 1 white flower. If this were to be a population of, let's say, 100 individuals, we would expect to have 75 of them have purple flowers and 25 of them being white flowers. So here's another example, and I want to pause the video for you here to see how you do on your very own hybrid cross here, dealing with cabbage butterflies, where white wings are dominant to yellow wings. Now, if we cross a heterozygote with a homozygous recessive individual, what are the genotypic and phenotypic ratios for their offspring? Pausing now. So parent number 1 being the heterozygote has a genotype of capital W, lowercase w, and parent number 2 being homozygous recessive has 2 lowercase w's in their genotype. If we put them in the cross right here in this Punnett square grid here, this 2 by 2, we can see that 1 box is going to cross the dominant with recessive for a heterozygous individual. Looks like this one's going to be 2 recessive alleles. This one's going to be a dominant allele and recessive allele. And this one's going to be a couple of recessive alleles as well. Counting up the number of genotypes we have, looks like we have 2 of the heterozygotes and 2 of the homozygous recessives. That's going to be a ratio of 1 to 1, really. And if we fill in the phenotypes of these, well, it looks like we have 2 whites to 2 yellows. That's going to be another 1 to 1 ratio. And looks like I was right with a 0 to 2 to 2, aka 1 to 1, 1 being the heterozygote and 1 being the homozygous recessive, 2 to 2, or 1 to 1 for the phenotype. Example number 2, we have black fur being dominant to white fur in mice. If we have a heterozygous mouse with a homozygous dominant mouse, we need to figure out the genotype and phenotype of those, or genotypic ratios and phenotypic ratios of those parents. Pause here for you so you can get over it. The parent here for parent number 1 is going to be a capital B, lowercase b, and parent 2 is going to be 2 capital B's. So if we cross those 2, you can see immediately there's going to be a lot of capital B's in here because each of these are going to have a capital letter inside them. In fact, it's going to be capital B, lowercase b, capital B, capital B, capital B, lowercase b. Looks like if we want to look at the phenotypes first, each and every one of these is going to be black because each of them have the dominant allele over the white fur. The genotype ratio looks like it's going to be another 1-to-1 ratio because there's two capital B to two capital B lowercase b. So that'd be a 2-to-2 to 0 ratio or a 1-to-1 to 0. You could also just write it 1-to-1 as long as you list the genotypes that are listed there. Capital B, lowercase b. And in this case, it would be a 1-to-0 ratio because every single one of them is black. You are not going to have any white mice forever given off of these two parents. Now, the next generation you could, because they have those recessive alleles behind there. But this generation here, this particular family of mice with the two parents here, is automatically going to have black mice no matter what, forever and ever. That's all I got for you. Good luck on activity 4.5. You're going to use your pedigree from 4.4 to cross together the family members of Hadiah's family. And then 4.6, you're going to do something very similar to this, but you will have to figure out the phenotype and genotypes of the parents before even starting the Punnett squares here.